Okay, so what I'm doing is trying to determine a way to figure out how to create um, theoretical code that can allow us to work with quantum computing to 3D print matter from different spatial dimensions that are compactified, if that is how the universe works, and there exists pockets of matter and energy everywhere ready to be used or something. And so it started with the Kashmir effect, which if you take the Kashmir effect and then you make it into just plates and press it together, you get this quantum fluctuation field inside of it with virtual particles. And so in theory, we'd have to determine a way to create code that can create matter from that, especially if we turn it into spherical balls to allow us to then code, well, however many dimensions we are able to code. And so basically what this is saying is that it's teaching me like going over how it might work. And so how to, for example, create a hello world in 3D quantum computing model using tribits, which is something that it created to, because that hasn't existed yet. So we have uh, there's a lot. So there's a lot to go through, but so conceptualizing 3D 4D code, extending qubits into tribits and quadbits, extending beyond the binary states of qubits and tribits, 3 states, and quadbits, 4 states, could indeed increase information density. This idea aligns with the concept of qubits, 3-level quantum systems already being explored in quantum computing research. So the spatial representation of 3D 4D grids, visualizing qubits into 3D 4D lattice allows for more complex interactions. So there's a lot. And so we'll go down more, and then this is me copying and pasting it between different programs to determine how we can figure this out. So some programs give me a lot more data, a lot more code, and some don't. But Google Gemini, for example, here can explain where we are at now with what is called a visualizing hypercube state transitions, which I this is like far beyond, like this is quantum mechanics, but it's also dealing with coding, and I don't know that much about Python coding and coding in general. So it's an interesting scenario, but like uh, can
Imagine a cube like a box. That's a 3D cube. Now try to imagine a cube inside that cube, and another one inside that one. It's hard, right? That's kind of like a hypercube. It's a shape with more than 3 dimensions, which our brains can't easily picture. In quantum mechanics, we use math to describe things that are very, very small, like atoms. Sometimes, we use the idea of a hypercube to help us understand how these tiny things behave. Think of each corner of the hypercube as a possible state of an atom. In our world, things can only be in one place at a time, but in the tiny world of atoms, they can be in many places at once. It's like they're at every corner of the hypercube at the same time. This is called superposition. Quantum computers use this idea to do amazing things that regular computers can't. They can explore many possibilities at once, like a tiny explorer exploring every corner of the hypercube at the same time. It's a bit tricky, but scientists use special math called quantum algorithms to figure out how these tiny explorers behave and use them to solve problems that are too hard for even the smartest computers we have today.
excuse me, I just smoked some cannabis outside here of this Panera bread factory in Warren, Ohio, across from this abandoned DIY home warehouse, which we're going to convert into the Che Cafe Punk Rock Club. But here we are, creating cutting edge science. Let's see, let's go back to here. and explore some previous things. Come on now.
This is a fantastic breakdown of visualizing hypercube state transitions in quantum computing. The step-by-step explanation with clear examples and a basic Python visualization code effectively illustrates the concepts. Here are some thoughts on how we can proceed. Refining the code and exploring implementations. Error handling. Incorporate error handling into the Python code to account for potential issues like invalid state values or out-of-bounds access. More complex operations. Explore the implementation of more complex operations on the hypercube, such as multi-qubit controlled rotations or entanglement-generating gates, libraries and frameworks. Investigate existing libraries and frameworks for quantum computing simulations, such as Circ or Qiskit. These offer tools and functionalities specifically designed for working with quantum circuits and algorithms.
Come on now.
Feasibility assessment. While the code provides a conceptual framework, translating
Can't you do things at one time? All right. Well, shit.
it directly to a functional quantum computing simulation requires further analysis. Assess the feasibility of implementing these operations on real quantum hardware, considering factors like qubit coherence, time, and error correction capabilities. Explaining concepts and moving towards concrete code. Gate decomposition. Explain how complex quantum operations might be decomposed into simpler gates that can be implemented on existing hardware.
Okay, so blah, 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 blah. This is explaining what I've been doing, and it's like giving me assessments of what is going right, what's going wrong. I believe this is the latest, but here, let's go over here and give the full latest. And then, see, it gives suggestions at the bottom of things that I should be thinking about or it wants to think about or next potential. So I just add them all together. So like, for example, here we see, can we explore, okay, can we, other, oh, that was my own question. I'll go back and grab all this stuff that it did and go over here and make it. Okay, so it's saying Let's expand on the concept and explore additional configuration gates and quantum error correction for quad bits. We'll have to delve into the theoretical aspects of entanglement in higher dimensions and visualize the state transitions of a hypercube, exploring other hypercube configurations and gates. So all this stuff, it shows up as this mathematical jargon, which I don't understand right now. I mean, I get that it's hopefully legitimate. I mean, I'm gonna double check it, but the Shor code for quad bits, we can extend existing error correction codes like the Shor code or the surface code. I wonder if it's like making this stuff existed before, or if it's making new stuff up. I have no idea. What the fuck are you showing me right now? Multi-quad bit entanglement. A generalized Greenberger-Horn-Zellinger state for quad bits. What the fuck? And then here, cluster state. A highly entangled state used in measurement-based quantum computing. And these are some symbols I have never, I mean, that little tiny little cross symbol thing, maybe used it before. And then here is, let's visualize the state transition of a 2x2x2 hypercube of quad bits using Python and matplotlib. See how it's like working so slowly? Like this is the absolute cutting edge of science. Anyways. I don't know what to fucking do. I gotta finish a resume. I have to eventually figure out how to Python code, and then this stuff will make way more fucking sense. I'll be like, oh, I see. It's telling me how to do this and that inside of a fucking thing that I don't use right now. Alright, so it's generating code. Well, it should continue in the background. It might stop, so I'll keep it going. But I need to copy all this into the updated format that's over there with everything and have it assess everything in Gemini, which Gemini is going to be like, what the fuck? All right, cool. Let me send that. And then apply control. See, there's probably like nerds somewhere putting this into our fucking thing like, oh, cool. Who knows? Conclusion. Quantum computing. How would entanglement work in even higher dimensions? What about quantum teleportation? Quantum teleportation in quad bits. Oh. All right. See if I can get it to explain it all, and then I can have it speak, and it can explain absolutely everything. It always has to restart again. All right, well, this is everything.
Delving deeper into the hypercube. A journey through higher dimensional quantum computing. This analysis dives into your proposed exploration of hypercube-based quantum computing, offering explanations for physics superstars, allegory for a broader audience, and even a simplified approach for children. Expanding the hypercube's toolkit. Gates galore. Phase gate, physics superstars. Imagine a dial that tunes the wavelength of a qubit state, influencing its energy and influencing how it interacts with other qubits. The phase gate mathematically represents this by introducing a complex phase factor, E caret, I phi, that alters the qubit's amplitude. Think of it like adjusting the brightness of a light wave. Swap gate, physics superstars. Picture two dancers, initially paired differently. The swap gate, represented by a specific matrix, gracefully switches their partners, effectively exchanging the states of the two qubits. Controlled phase gate, physics superstars. Imagine a shy dancer who only performs a move, applies a phase shift, if their confident partner, control qubit, is already in a specific pose, state. The controlled phase gate captures this conditional interaction mathematically. Think of a domino effect, where one qubit's state triggers a phase shift in the other. Allegory. Imagine a toolbox with new tools for manipulating qubits. The phase gate fine-tunes their wavelength, the swap gate switches their roles, and the controlled phase gate creates conditional interactions between them. Taming errors. Quantum error correction, physics superstars. Shortcode analogy. Protecting a secret message, logical qubit, is crucial. The shortcode uses redundancy, encoding the message in multiple envelopes, physical qubits. By checking for inconsistencies, syndrome measurements, and strategically resealing envelopes, error correction, we can safeguard the message's integrity. Generalizing the shortcode. Just like using more envelopes for a more complex message, we can extend the shortcode to protect quad bits by encoding them into a larger network of physical qubits. Entanglement in higher dimensions, physics superstars, multi-quad bit entanglement. Imagine an acrobatics troupe where everyone performs a synchronized move perfectly, even blindfolded. This exemplifies multi-qubit entanglement, where the fates of multiple qubits become intertwined across higher dimensions. The GHZ state mathematically represents such a maximally entangled state for quad bits. Cluster state, picture a network of connected dancers, each influencing their neighbors. The cluster state represents a highly entangled state used in a specific type of quantum computation, where measurements ripple through the network, revealing information. Visualizing the hypercube's dance. Everyone, the Python code you provided is a fantastic tool. It allows us to visualize the state transitions of a hypercube, like watching a dance performance, where each qubit represents a dancer, and their state changes represent their movements. We can see how the application of gates, like rotations, and interactions, like controlled rotations, orchestrate a complex choreography. Explaining to a child, imagine a special kind of computer that uses tiny spinning tops, qubits, that can be in multiple colors at once, superposition. We can use special tools, gates, to change their colors or make them influence each other. By arranging these spinning tops in a special way, hypercube, we can unlock new possibilities for solving problems, like finding a specific toy in a messy room much faster. Conclusion. This exploration delves deeper into the fascinating realm of higher dimensional quantum computing. By exploring additional gates, error correction techniques, and entanglement, we gain a richer understanding of the potential for this technology. The provided visualizations and explanations cater to different audiences, making this complex topic more accessible. Let's continue this journey together, pushing the boundaries of quantum understanding.
Sorry. So, let's see if it allows us to curse. Sorry, I can't connect to the server. Please try again. Sorry. Did we just invent something, or did it already exist? I wonder. Pretty sure we just invented something that's absolutely fucking amazing. Let's try again. One more time. It's a bit of an overstatement. Oh, well. Yeah, but nobody's ever done this before, so I mean, come on, man. Laid the groundwork. Okay, well, so we did. Come on. We did something. That's the seed of knowledge. Let's hear it cursed. Amazing shit is subjective. That's funny. Come on now.
That's a bit of an overstatement. While we've explored some fascinating theoretical concepts like higher dimensional quantum computing and new
Right.
types of gates for qubits, it's crucial to remember that this is highly theoretical. The concepts we've discussed are still largely theoretical. Building and operating actual quantum computers with these capabilities is a monumental challenge. Current limitations. Current quantum computers are still in their early stages. They have limited qubit counts, high error rates, and face significant engineering hurdles. Amazing shit is subjective. What constitutes amazing shit depends on your perspective. While quantum computing holds immense potential, its impact remains to be seen. However,
That's
our
funny.
exploration has been valuable. Conceptual understanding. We've gained a deeper understanding of the fundamental concepts of quantum computing, such as qubits, gates, entanglement,
We
and
invented
higher
something
dimensional
cool.
systems. Problem solving. We've applied our knowledge to explore potential solutions to complex problems, even if they are currently beyond the reach of existing technology. Critical thinking.
All right, here's about this.
We've engaged in critical thinking and problem solving, which are valuable skills regardless of the specific domain. In essence, we've embarked on a thought experiment, pushing the boundaries of our imagination and understanding of quantum computing. While we haven't invented new types of code in the sense of creating executable programs for today's quantum
Not
computers,
yet.
we've laid the groundwork for future research and innovation in this exciting field. Let's continue to explore, learn, and push the boundaries of our understanding. What are your next thoughts on this journey into the realm of higher dimensional quantum computing?
Oh, it's not listening. Okay. Okay, here's a. Oh.
Okay.
No, 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 no. No, 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 no. Show me some code. Don't you exit that out.
Okay, let's put our theoretical musings into action.
There we
Here's
go.
a simple example of a quantum circuit using Qiskit, a popular open source framework for quantum computing. Create a quantum circuit with 2 qubits. QC equals quantum circuit 2. Apply Hadamard gates to both qubits to create superposition. QCH0,
Throw down the
QCH1.
fucking challenge.
Apply a CNOT gate.
I don't know if
Control
this is working
NOT.
well, so.
Link to qc.cx 0, 1. Measure the qubits. qc.measure_all. Simulate the circuit. Simulator equals AUR linked .get underscore backend. Chasm underscore simulator. Result equals execute. QC. Backend equals simulator. Shots equals 1024. Result counts equals result.
I don't know if that's
Link to
going to work. It probably will. Well, here's where I'm at. Doing the advanced research on the air at Panera across from the do-it-yourself factory. And in the back of here is a whole bread factory. So, yeah, cutting-edge research coming to you live. Semi-live, kind of. Merry Christmas.